Imagine sitting in front of a modern computer and moving a file several gigabytes in size from one drive to another. A high-performance NVMe solid-state drive can complete the transfer so quickly that the progress indicator may barely remain on screen long enough to register. Games containing tens of gigabytes are installed routinely, operating systems occupy more space than entire computer collections once possessed, and a storage device smaller than a stick of chewing gum can hold thousands of photographs, hundreds of hours of audio, enormous software libraries, and years of personal documents. That experience has become ordinary enough that the technology behind it is easy to overlook. Yet only a few decades earlier, personal computer users lived in a completely different world. Saving information meant handling physical disks, listening to motors turn, waiting for mechanical heads to locate magnetic tracks, and sometimes discovering that a program simply would not fit on the storage available. In that era, a few hundred kilobytes could represent meaningful computing capacity. A single megabyte was substantial. The idea that a consumer computer might one day move billions of bytes every second would have sounded less like an engineering forecast than a description of an entirely different machine. To understand how storage crossed that enormous distance, it is necessary to return to a time before the personal computer had settled on what permanent storage was supposed to look like. Long before computers reached bedrooms, school desks, and small offices, storing digital information was already a central problem of computing. Early machines could calculate at remarkable speed for their time, but calculation alone was not enough. Instructions had to be entered, results had to be preserved, and information needed some physical form that could survive after a machine stopped running. Punched cards became one answer. Data was represented by patterns of holes cut into stiff paper cards, creating a physical record that could be sorted, stacked, transported, and fed into machines. For institutions accustomed to enormous rooms filled with equipment and trained operators, cards were practical enough, but they were hardly suited to the emerging idea of a computer sitting beside one person. Magnetic tape offered another approach. It could hold much more information and became essential for backup and large-scale data processing, although finding a particular piece of information often required moving through the tape sequentially. That characteristic was acceptable for certain jobs, but inconvenient when a computer needed quick access to files scattered across a storage medium. Large disk systems eventually provided faster random access, yet early examples were expensive, physically substantial, and designed for organizations with resources far beyond those of a hobbyist buying a microcomputer. When small computers began appearing in the 1970s, their limited storage reflected both the economics and the scale of the machines themselves. Many early systems relied heavily on volatile memory, meaning that information disappeared when power was removed unless it had been saved somewhere else. Some hobbyists used paper tape. Others used ordinary audio cassettes because tape recorders were inexpensive and already widely available. A program could be converted into tones, recorded onto cassette, and later loaded back into the computer. The method was clever because it transformed a common household device into digital storage, but convenience was relative. Loading could be slow, reliability depended on recording quality and hardware adjustment, and locating one program among many was not as effortless as selecting a modern file from a directory. Still, these limitations made sense in a world where software itself remained comparatively small. Early personal computers did not need to store high-resolution photographs, compressed movies, sprawling game worlds, or operating systems containing millions of files. A useful program might occupy an amount of memory that would be trivial today. As personal computing grew more ambitious, however, software began demanding a storage medium better suited to repeated use. The floppy disk became one of the most important answers. Its origins belonged to the world of larger computer systems, but its design proved exceptionally well matched to the developing personal computer industry. At the center of a floppy disk was a thin circular sheet coated with magnetic material. When the disk rotated inside a drive, a read and write head could detect or alter magnetic patterns representing digital information. Data was arranged in tracks and sectors, allowing the computer to reach particular areas without processing everything that came before them. That ability made the floppy fundamentally different from a cassette tape. Instead of waiting for a long sequence to pass, software could request information from a specific location on the disk. Early floppy formats were physically large by later standards. 8-inch disks appeared first, followed by the 25-inch format that became closely associated with the early personal computer era. The smaller size was not merely cosmetic. It reflected a broader transformation in computing as equipment designed for institutions gave way to devices intended for desktops. A 5.25-inch floppy was flexible enough to bend inside its protective sleeve, which is where the familiar name came from. Users handled it carefully, sliding it into a drive and securing it with a latch or lever. Once the machine began reading, the drive produced a distinctive mixture of spinning, clicking, and stepping sounds. Those noises were not artificial feedback. They were the audible consequence of mechanical work taking place only centimeters from the user. The motor rotated the disk, while the drive mechanism positioned the head over the required track. For people encountering personal computers during this period, the sound became part of computing itself. More important than the sensory experience was what the floppy made possible. Software could now be distributed on inexpensive removable media. A user could purchase a program, bring it home, insert the disk, and load it without entering pages of code manually. Documents could be saved and carried to another computer. Schools could distribute educational programs. Businesses could exchange files without moving entire machines. Hobbyists could share software through physical copies. The floppy disk, therefore, did more than increase storage capacity. It gave digital information a practical portable form at exactly the moment personal computing was expanding beyond laboratories and specialist clubs. Capacity, nevertheless, remained restrictive. A disk holding a few hundred kilobytes could seem generous when many programs were small, but software did not remain small for long. Better processors encouraged developers to create more capable applications. Graphical interfaces required additional resources. Games gained larger maps, more detailed artwork, and richer sound. Business software expanded in complexity. Operating systems accumulated features. Storage capacity increased as floppy technology improved, yet demand kept moving with it. The 3.5-inch floppy, which became widespread later, enclosed the magnetic disk in a rigid plastic shell that offered better physical protection and greater convenience. Common high-density versions used on PCs eventually held 1.44 megabytes. For its time, that capacity was useful enough to become a standard part of everyday computing. For modern users, however, the number reveals how radically expectations have changed. A single photograph from a contemporary camera can easily require more space than several such disks. A modern operating system installer would need not a handful of floppies, but thousands. Even during the floppy era, users increasingly experienced the practical limits firsthand. Installing a substantial application might involve feeding multiple disks into the computer in sequence. The software would read one, stop, and request another. The user removed the first disk, inserted the next, and repeated the process. A missing or damaged disk could interrupt the entire installation. Copying large collections required patience. Important files had to be organized with an awareness that every disk represented a hard physical ceiling. Labels mattered because storage was something a person could literally hold, misplace, stack, damage, or accidentally overwrite. The humble disk box became a part of the personal computing landscape because data management was still partly a physical activity. At the same time, the existence of removable storage changed what people expected from computers. Once users could save programs and documents reliably, they wanted to keep more of them. Once software companies could distribute increasingly complex products, they wanted room to build even larger ones. Once businesses began treating personal computers as serious tools, repeatedly swapping small disks started to feel inefficient. The floppy had solved the immediate problem of portable digital storage, but its success helped expose a larger need. A computer that was becoming central to office work, creative tasks, entertainment, and personal organization required a place where substantial amounts of information could remain available without constant intervention. Engineers already knew of a technology capable of providing that kind of capacity. Hard disks had existed for years in larger computer systems, where rigid magnetic platters stored far more data than flexible, removable media. The obstacle was bringing that machinery down to a size, price, and level of reliability suitable for personal computers. Doing so required far more than shrinking an existing product. A hard drive depended on precise mechanical relationships between spinning platters, moving heads, motors, electronics, and an enclosure designed to protect an environment where microscopic positioning errors could destroy data. The components had to become smaller while tolerances became more demanding. Costs had to fall while capacities rose. What had once belonged to expensive institutional computing needed to become something an ordinary PC owner could install inside a metal desktop case. By the beginning of the 1980s, the direction of the industry was becoming clear. Floppy disks would remain indispensable for software distribution and file exchange, but they could no longer carry the entire burden of personal storage. Programs were growing, users were producing more data, and the computer was beginning to evolve. From a machine that temporarily loaded information into a machine expected to remember a growing portion of a person's digital life. The next transformation would take place behind the front panel, inside the computer itself, where spinning rigid platters would turn permanent storage from something users repeatedly inserted into something they increasingly expected to be there the moment the machine started. The hard drive changed the role of storage because it no longer depended on the user to insert the medium every time information was needed. Instead of treating data as something temporarily brought into the machine, the personal computer could begin to maintain a substantial collection of programs and files internally. The basic idea behind the hard disk was not new. IBM had demonstrated magnetic disk storage decades earlier, when the equipment was large, expensive, and intended for institutional computing. What changed over time was the ability to compress that same general principle into a package suitable for a desktop machine. Inside a hard drive, one or more rigid platters coated with magnetic material rotated at high speed around a central spindle. A precisely controlled actuator moved read and write heads across their surfaces, allowing the electronics to locate specific regions of stored data. The mechanism sounds straightforward when described in broad terms, yet reliable operation depended on extraordinary accuracy. The heads had to pass extremely close to the surface without touching it during normal operation, while the drive continuously managed vibration, rotational stability, positioning, heat, contamination, and the possibility of mechanical wear. A tiny error could corrupt information. A larger one could damage the storage surface itself. Bringing such a device into the personal computer market, therefore, demanded a combination of mechanical engineering, manufacturing precision, electronic control, and declining component cost. During the late 1970s and early 1980s, those conditions began to converge. The arrival of smaller hard disk form factors was especially important. Drives no longer had to resemble equipment built for mainframes or mini-computers. Companies could produce units compact enough to fit within systems designed for individual users. One of the important developments came from the shift toward the 5.25-inch hard drive format, which aligned naturally with the dimensions already familiar from floppy drives. This made it easier for computer manufacturers to imagine rigid disk storage, not as an external industrial device, but as an internal component of a personal machine. Early examples offered capacities that seem almost negligible today, yet at the time they transformed what a microcomputer could do. A hard drive, storing a few megabytes, represented a remarkable improvement over removable disks, measured in hundreds of kilobytes. Instead of choosing which handful of programs to keep immediately available, a user could maintain an operating system, business applications, utilities, documents, and other files on the same machine. The improvement was not only numerical, it altered behavior. When storage became persistent and internally accessible, users stopped thinking of every program as something that had to be physically brought to the computer before use. Software could remain installed. Files could be organized into directories rather than separated primarily by which disk happened to contain them. The machine began to feel less like a device that temporarily performed tasks, and more like a personal environment capable of accumulating information over time. The IBM PC helped bring this shift into mainstream business computing. The original 1981 model was commonly configured around floppy drives, but the demand for larger internal storage grew quickly as the platform gained popularity. When IBM introduced the PCXT in 1983, one of its defining features was an internal hard disk with a capacity of 10 megabytes. That figure needs to be understood in the context of the period rather than compared casually with modern storage. 10 megabytes meant that a user could keep an amount of information inside one machine that would otherwise require a substantial collection of floppy disks. Programs did not need to be constantly exchanged in and out of the drive. Business records could stay on the system. The operating environment became more convenient because storage was available immediately after startup. For organizations adopting PCs as serious workplace tools, that convenience was not a luxury. It reduced the friction of daily use. Yet the early hard drive experience also introduced users to a new kind of dependency. A floppy disk could be removed and stored elsewhere. An internal hard drive concentrated more information in one place, which made failure more consequential. Mechanical drives could develop problems in motors, heads, bearings, electronics, or magnetic surfaces. A system that appeared to contain an entire office's working memory could suddenly become inaccessible. Backup therefore grew in importance alongside capacity. The more useful hard drives became, the more painful their loss could be. Storage progress was beginning to create risks that earlier users had encountered on a smaller scale. As personal computers spread through offices and homes, capacity demands accelerated. Software companies took advantage of the additional room. Programs became more sophisticated because developers no longer had to assume that every application would be squeezed into an extremely small removable disk. Databases expanded. Word processors gained features. Spreadsheet software became more capable. Graphics applications appeared. Operating systems grew more complex as hardware support increased. The growth was gradual enough that each generation seemed practical when it arrived, but across a decade the change was substantial. Hard drives that once offered 5 or 10 megabytes gave way to capacities measured in tens of megabytes, then hundreds. By the 1990s, drives crossing the 1 gigabyte threshold became realistic for personal systems. A storage quantity that had once belonged to far more expensive computing environments moved toward ordinary consumer machines. That expansion depended heavily on increasing areal density, the amount of data stored within a given physical area of the platter. Engineers improved magnetic materials, head technology, signal processing, servo control, and manufacturing tolerances so that bits could be packed more closely together. As those bits became smaller, the drive had to distinguish extremely subtle magnetic patterns while positioning the head with increasing precision. Higher density made greater capacities possible without requiring drives to grow larger in proportion. In many cases, physical dimensions actually became more standardized even while the amount of stored information increased dramatically. The progress could appear almost magical from outside the sealed enclosure, but inside the mechanism, the margin for error was becoming narrower. The read and write head did not simply hover over a broad region of the disk. It had to follow tracks that became progressively tighter as storage density increased. The servo system responsible for positioning the actuator therefore became critical. Changes in temperature, vibration from other components, manufacturing imperfections, or mechanical shock all had to be managed within tolerances that would have seemed extreme in earlier generations. The drive's electronics increasingly participated in this process, interpreting signals, correcting errors, mapping defective sectors, and presenting the computer with a cleaner abstraction than the raw physical medium beneath it. To the operating system, storage appeared as ordered blocks of information. Beneath that simplicity, the hardware was performing constant mechanical and electronic coordination. Interface technology evolved alongside the drives themselves. Early PC hard disks often relied on separate controller hardware and standards that required a relatively complex relationship between the drive and the host system. As the market matured, manufacturers sought simpler and more integrated approaches. The emergence of IDE, commonly associated with the broader ATA family, moved much of the drive control functionality onto the drive itself. Instead of relying on a separate controller to manage many of the low-level details, the storage device could handle more of that work internally. This helped simplify system design and contributed to the standardization of hard drive installation across a rapidly expanding PC market. The ribbon cables and connectors of the era became familiar sights inside desktop cases, linking storage devices to the motherboard while power arrived through a separate connection. For users who upgraded their own computers, installing a hard drive involved more than simply fastening it in place. Drives might need to be configured as master or slave when two devices shared the same channel. Jumpers on the drive selected operating modes. BIOS settings could require attention. Capacity limits sometimes emerged from older software assumptions or firmware designs that had not anticipated how quickly storage would grow. These constraints provide an important reminder that the history of storage was never driven by the media alone. A drive could physically hold more data than a system was prepared to address. Interfaces, firmware, operating systems, file systems, and application software all had to evolve together. The expansion of hard disk capacity also coincided with a broader transformation in what personal computers were expected to contain. Early users had mainly stored programs and relatively small documents. By the 1990s, multimedia had begun to change the equation. Graphical operating systems required larger installations. Sound files became common. Digital images demanded substantially more space than text. CD-ROM software encouraged applications to include richer artwork, audio, video, and large reference databases. Computer games expanded from compact programs into elaborate productions containing detailed graphics, recorded music, voice acting, and increasingly complex environments. A hard drive that once appeared generous could become crowded after only a few years, because the definition of a normal file had changed. Storage manufacturers responded with larger drives, and software developers quickly found uses for the additional capacity. This cycle became one of the defining patterns of personal computing. More storage did not permanently solve the problem of insufficient capacity. Instead, increased capacity enabled new forms of software, which then raised expectations and created demand for still more space. The pattern repeated as drives moved from megabytes into gigabytes and eventually toward terabytes. A similar process occurred with performance. Greater capacity was valuable, but users also wanted quicker access. Mechanical drives could improve through faster spindle rotation, better actuators, larger caches, smarter firmware, and more efficient interfaces. Common desktop drives often operated at rotational speeds such as 5,400 or 7,200 revolutions per minute, while performance-oriented models could spin faster. Reducing seek time allowed the head to reach the required track more quickly. Larger caches temporarily held frequently accessed information. Improved controllers optimized command handling. Even so, every request for data remained tied to physical motion. If the necessary information was not already available in cache, the actuator had to move, the platter had to rotate to the appropriate position, and the head had to wait for the relevant sector to pass beneath it. For sequential transfers, where large blocks of information were stored close together, mechanical drives could perform reasonably well. Random access exposed their deeper weakness. A computer might need thousands of small files scattered across different physical regions. Each movement consumed only a fraction of a second, but enough of those fractions accumulated into noticeable delay. Users rarely described the experience in technical terms. They noticed that the machine took time to start. Programs opened slowly. A busy drive produced continuous mechanical noise while the computer seemed unresponsive. The small indicator light on the case remained illuminated as the device worked through requests. Some of the most familiar rituals of the hard drive era grew directly from these limitations. Disk defragmentation, for example, became a routine maintenance task on many systems. As files were created, deleted, and modified, parts of a single file could become scattered across different regions of the disk. The drive then had to perform additional head movement to retrieve those fragments. Defragmentation attempted to reorganize them into more contiguous arrangements, reducing unnecessary seeking and improving access in certain workloads. And the process could take considerable time, particularly on large or heavily fragmented disks. Its very existence reflected the mechanical nature of the medium. The user was not merely reorganizing abstract information. Software was rearranging the physical placement of data so that moving hardware could reach it more efficiently. Despite these disadvantages, magnetic hard drives remained remarkably successful because they offered an increasingly attractive combination of capacity and price. Manufacturing improved, competition intensified, and the cost per stored megabyte fell dramatically. Consumers could purchase larger drives without paying proportionally more each time. This economic advantage proved essential. Even when alternative forms of electronic storage existed, they could not immediately compete with hard disks for large quantities of affordable capacity. The spinning platter therefore survived repeated predictions that another technology would soon make it obsolete. It continued to evolve because engineers repeatedly found new ways to increase density, refine mechanics, and reduce cost. By the turn of the century, personal computers commonly contained hard drives holding many gigabytes. Not long afterward, capacities reached into hundreds of gigabytes. Terabyte-class drives eventually became ordinary consumer products. The transformation from the 10 megabyte hard disk of an early IBM PC XT to drives holding trillions of bytes happened within a few decades. Yet the essential mechanical principle remained recognizable throughout that period. Platters rotated, heads moved, magnetic patterns represented data. The sophistication surrounding those actions became extraordinary, but the machine still depended on motion. That dependence mattered more as other parts of the computer accelerated. Processors executed instructions at speeds that increased dramatically. System memory became faster and larger. Graphics hardware developed into powerful parallel processors. Software demanded rapid access to enormous collections of files. Hard disks continued improving. Yet the difference between electronic processing speed and mechanical access time became harder to ignore. The storage device was no longer merely a place where information lived. In many situations, it had become the component determining how long the rest of the system had to wait. Engineers had pushed spinning magnetic storage through decades of extraordinary refinement, but every improvement was still negotiating with the same physical realities. Mass had to move, a platter had to rotate, and a head had to reach the right place before the requested information could be delivered. That mechanical delay became increasingly visible as personal computers entered an era in which almost every other major component was accelerating through electronic rather than physical means. A processor could execute enormous numbers of instructions while waiting for a hard drive to reposition its head. System memory could respond in a tiny fraction of the time required for a mechanical seek. Graphics processors were beginning to handle workloads that would once have seemed impossible on a desktop machine. Yet opening an application could still produce several seconds of audible disk activity before anything useful appeared on screen. The imbalance did not mean that hard drives had stopped improving. On the contrary, manufacturers continued refining them with remarkable determination. Faster spindle speeds reduced rotational delay. More precise actuators shortened seek times. Larger caches allowed frequently requested data to be delivered without returning immediately to the platter. Firmware became increasingly sophisticated, predicting access patterns, arranging commands more efficiently, correcting errors, and concealing many physical imperfections from the operating system. Interfaces advanced as well, increasing the amount of data that could move between the drive and the rest of the computer. Yet these improvements were working around a fundamental characteristic that no controller could completely eliminate. A mechanical disk needed time to move. The distinction between sequential and random access made this limitation particularly important. If a computer requested a large file stored in a continuous region, the head could remain relatively stable while the platter passed data beneath it, allowing the drive to transfer information at a respectable rate. The situation changed when an operating system or application demanded thousands of small pieces scattered across different locations. Each request might force the actuator to reposition. Even if one movement required only a few milliseconds, repeated seeks accumulated quickly. Modern software increasingly depended on exactly this kind of workload. Starting an operating system involved accessing libraries, configuration files, drivers, logs, user settings, executables, and many other small components. Launching a complex program could produce another storm of requests. The user experienced the result not as an engineering measurement, but as waiting. A desktop appeared while background processes continued loading. An application window opened but remained unresponsive. A game paused at a loading screen while the drive searched for textures, audio, level data, and executable resources. The computer might have been capable of processing that information almost instantly once it reached memory, but the storage system still had to physically find it. Interface development attempted to make sure that the connection itself did not impose unnecessary restrictions. Parallel ATA, widely known through the IDE terminology used throughout the PC industry, served personal computers for years and evolved through progressively faster modes. It was practical, inexpensive, and deeply embedded in desktop hardware, although its broad ribbon cables and shared channel arrangements reflected an older generation of system design. As drive performance and computer architectures advanced, a replacement emerged. Serial ATA, or SATA, changed the physical and electrical connection between storage and the motherboard. Instead of the wide parallel ribbon cable associated with earlier drives, SATA used a much narrower cable and a serial communication method that could scale to higher signaling rates while simplifying internal cabling. The first generation provided bandwidth beyond what most consumer mechanical drives could fully exploit in normal use. Later versions raised the ceiling further. SATA 2 increased the signaling rate, and SATA 3 eventually provided a theoretical link of 6 gigabits per second, enough for roughly 600 megabytes per second of raw transfer capacity before protocol overhead was considered. For spinning disks, this was more than sufficient for many years, because the mechanical medium itself remained the slower part of the chain. That distinction is essential. A faster interface does not automatically make stored information arrive faster if the device behind it cannot supply data at the same rate. A road can be widened, but a vehicle still travels according to its own limits. Mechanical drives benefited from improved interfaces because command handling became cleaner and peak transfers could rise, but the latency created by moving components remained. Increasing rotational speed offered one possible response. Drives spinning at 7,200 revolutions per minute became common in performance-oriented desktop systems, and models operating at 10,000 revolutions per minute or more appeared in specialized markets. Faster rotation reduced the average time required for a desired sector to arrive beneath the head and could increase sustained transfer performance. The improvement came with trade-offs. Higher rotational speeds could generate additional heat, noise, vibration, and power consumption. Precision became more demanding as mechanical forces increased. These were not insurmountable problems, but they illustrated the physical price of making a rotating device respond more quickly. Hard drive engineers were extracting greater performance from an architecture that had already undergone decades of refinement, and every incremental gain required increasingly careful control of a machine operating within extremely small tolerances. Meanwhile, the nature of personal data was changing again. Broadband internet allowed users to download files that would once have been impractical to transfer. Digital cameras produced growing collections of photographs. Compressed music libraries accumulated on home computers. Video editing moved beyond specialist studios. Games expanded dramatically as developers incorporated detailed environments, recorded dialogue, orchestral soundtracks, high-resolution textures, and cinematic sequences. Operating systems became larger because they supported more hardware, richer graphical interfaces, networking, security features, multimedia frameworks, and increasingly complex background services. The amount of storage required by ordinary computer ownership rose, but capacity was only part of the pressure. Users wanted immediate access to that expanding collection. A drive could hold hundreds of gigabytes and still make the computer feel slow if retrieving scattered information required constant mechanical seeking. Laptop computing exposed another weakness of spinning storage. A desktop hard drive usually remained stationary inside a case, but a portable computer could be carried, tilted, bumped, or dropped. Manufacturers developed protective features and increasingly robust mechanisms, yet the presence of delicate moving components created an unavoidable vulnerability. A sufficiently severe impact during operation could cause damage. Power consumption also mattered more in battery-powered systems, where spinning a motor continuously consumed energy that designers wanted to conserve. Noise, once accepted as a normal characteristic of computing, became more noticeable as laptops and compact desktops grew quieter. These pressures encouraged interest in storage that could retain data without depending on rotating media. Electronic, non-volatile memory had existed in various forms for years, but early implementations were too expensive, too limited in capacity, or otherwise unsuitable to displace the hard disk in an ordinary personal computer. Flash memory gradually changed the possibilities. Unlike conventional system RAM, which loses its contents when electrical power disappears, flash can preserve stored information after shutdown. It does so without a spinning platter or moving head. Data is represented through electrical states within semiconductor cells, allowing the device to access information electronically. The absence of mechanical positioning meant that random access could occur far more quickly than on a hard disk. A request for one piece of data did not require a head to travel across a physical surface and wait for rotation. The storage controller could reach memory locations through electronic operations, whose timing belonged to a completely different scale. Flash was already becoming familiar outside desktop computers before solid-state drives reached a mass audience. Memory cards appeared in digital cameras and portable electronics. USB flash drives offered a convenient replacement for many tasks once performed by floppy disks. Small removable devices could carry documents between computers without motors, exposed magnetic media, or the limited capacity of the old 3.5-inch disk. Each of these products helped normalize the idea that substantial information could live inside semiconductor memory rather than on something that physically rotated. The transition still faced a severe economic obstacle. Magnetic hard drives had benefited from decades of manufacturing improvements and could provide enormous capacity at comparatively low cost. Flash memory was substantially more expensive per unit of storage. Early solid-state devices therefore made the most sense where silence, shock resistance, power efficiency, or low access latency justified the price. High-performance computing, industrial systems, specialized equipment, and premium portable computers could adopt the technology before the average desktop user was ready to pay for it. Capacity was another concern. A consumer could buy a hard drive large enough to hold an extensive media library for far less money than an SSD of comparable size. The replacement of spinning disks would therefore not happen simply because flash was technically faster. It required a wider ecosystem of semiconductor manufacturing, controller development, error correction, wear management, interface support, and falling cost. Flash memory also brought limitations of its own. Its cells could not be written indefinitely without degradation. Data generally had to be erased in larger blocks than the small units in which it might be read, complicating updates. The controller needed to distribute writes so that the same physical cells were not exhausted prematurely, a technique known as wear leveling. Error correction methods became increasingly important as manufacturers pushed more information into each cell and increased storage density. The SSD that eventually appeared to the operating system as a simple disk was therefore anything but simple internally. Behind that abstraction, controllers continuously managed where information was placed, which cells were available, how writes were distributed, how errors were corrected, and how unused blocks could be prepared for future operations. These mechanisms allowed flash to behave like familiar storage while exploiting characteristics that were fundamentally different from magnetic disks. As the technology matured, the contrast in everyday responsiveness became difficult to ignore. A computer equipped with an early consumer SSD might not necessarily have offered enormous capacity, but tasks dominated by random access could feel transformed. Booting the operating system required less waiting because thousands of small files could be retrieved without mechanical seeks. Applications launched more rapidly. Multitasking became smoother when the system needed to access storage repeatedly. Searching directories, opening documents, and loading program components could happen with a responsiveness that benchmark numbers alone did not fully convey. For years, users had often responded to a sluggish computer by purchasing a faster processor or adding memory. The arrival of practical SSDs revealed that storage latency had been responsible for a much larger share of the perceived delay than many consumers realized. This did not immediately end the hard drive era. Instead, personal computing entered a transitional period in which the two technologies frequently shared the same machine. An SSD with modest capacity could contain the operating system and commonly used applications, delivering fast startup and responsive daily operation, while a much larger hard drive stored photographs, videos, games, archives, and backups at a lower cost per gigabyte. The arrangement was a compromise shaped by economics rather than engineering preference. Users placed the data that benefited most from speed on solid-state storage and the data that mainly required space on magnetic platters. As flash prices declined and capacities increased, that compromise gradually shifted. The solid-state drive was no longer merely a specialized component for enthusiasts or expensive laptops. It was becoming a realistic replacement for the device that had defined personal computer storage for decades. Yet the first wave of mainstream SSDs inherited something from the mechanical world they were beginning to displace. Many connected through SATA, an interface created during an era when rotating disks determined the pace of storage. At first, this was convenient because computers already supported the standard, and SSDs could be installed as direct replacements for hard drives. Soon, however, the advantages of flash created an unexpected reversal. Instead of waiting for the storage medium to catch up with the interface, increasingly fast solid-state memory began approaching the limits of the connection itself. The bottleneck was moving away from the device and into the path that carried its data. Once solid-state storage began approaching the limits of SATA, the history of PC storage entered a new phase. For the first time in the consumer market, the storage medium itself was becoming fast enough that the interface around it could hold it back. This was a striking reversal. Mechanical drives had spent years struggling to deliver data quickly enough to use all of the bandwidth available to them. Flash-based devices now presented the opposite problem. Their electronic access was so rapid that a connection designed during the hard drive era could become the restrictive part of the system. Before that limitation could be overcome, however, the SSD first had to become mature enough for ordinary users to trust. Early consumer models demonstrated impressive responsiveness, but performance alone was not sufficient. Buyers also cared about durability, consistency, capacity, compatibility, and price. Flash memory presented challenges very different from those faced by magnetic disks. A hard drive could rewrite a sector repeatedly through changes in magnetic orientation. NAND flash required more complicated erase and programming behavior, and its cells gradually wore as they were subjected to repeated program and erase cycles. A reliable SSD therefore depended heavily on intelligence built into its controller. That controller became one of the most important components in the device. It determined where data should be written, distributed activity across available flash cells, corrected errors, communicated with the host computer, maintained mapping information, and attempted to preserve long-term performance even after the drive had been used heavily. To the operating system, an SSD still looked like an orderly collection of addressable storage locations. Internally, those logical addresses could be redirected continuously as the controller moved information around the flash memory. This distinction mattered because the operating system did not need to know the exact physical cell containing every byte. The controller maintained translation tables that connected logical requests from the computer to the changing physical arrangement inside the drive. Such abstraction gave SSD designers flexibility to compensate for the limitations of NAND, where leveling spread writes across the memory rather than repeatedly exhausting one region. Bad blocks could be retired from service. Spare capacity could be reserved to support internal management. Garbage collection consolidated valid data so that entire blocks could be erased and prepared for future writes. None of these operations were obvious to someone opening a document or starting a game, yet they determined whether the SSD remained responsive after months or years of use. Another important development involved communication between the operating system and the drive. When a user deleted a file, a traditional hard disk could simply mark the corresponding sectors as available because rewriting magnetic storage did not require those sectors to be erased in advance. Flash behaved differently. The SSD benefited from knowing which blocks of data were no longer needed so that it could prepare them efficiently for future writes. The trim command allowed an operating system to inform the SSD that certain logical blocks had been discarded. With this information, the controller could manage unused flash more intelligently. Features like trim rarely appeared in advertisements with the same excitement as headline transfer speeds, but they helped turn SSDs from impressive demonstrations into dependable everyday storage. At the same time, NAND technology itself continued evolving. Early solid-state drives often relied on flash cells storing relatively limited amounts of information per cell. Manufacturers then developed ways to encode more bits into each cell, increasing capacity without requiring a proportional increase in silicon area. The industry moved through designs commonly described as single-level, multi-level, triple-level, and later quad-level cells. Each step improved density and helped reduce cost per gigabyte, but also made the job of accurately distinguishing electrical states more demanding. A cell representing 1 bit required fewer voltage levels than a cell representing multiple bits. Packing more information into the same physical structure increased the number of states that the controller had to identify correctly, while endurance and raw performance characteristics could also change. The solution was not simply better memory. Improved error correction, more advanced controllers, caching techniques, over-provisioning, and increasingly sophisticated firmware allowed consumer drives to offer large capacities at prices that continued to decline. The physical construction of NAND also changed. Traditional flash fabrication arranged cells largely across a flat silicon surface, but shrinking those structures indefinitely became difficult. Manufacturers increasingly turned to three-dimensional NAND, stacking layers of memory cells vertically. Instead of depending only on making every feature smaller in 2 dimensions, engineers could build upward. This approach opened another path toward greater density and helped support the growth of high-capacity SSDs. A device occupying the same general footprint could contain substantially more flash as layer counts increased and manufacturing processes improved. For consumers, these changes appeared gradually as higher capacities moved into affordable price ranges. Drives that had once seemed financially reasonable only at modest sizes became available with hundreds of gigabytes, then 1 terabyte and beyond. The shift altered purchasing decisions. During the earlier transition period, many enthusiasts had accepted the compromise of a small SSD for the operating system and a large hard drive for everything else. As flash became cheaper, the dividing line moved. Games could stay on the SSD. Large application libraries followed. Eventually, many laptops abandoned mechanical storage entirely because a sufficiently large solid-state drive could satisfy both performance and capacity requirements without the weight, noise, vibration, and power draw of a spinning disk. Desktop systems retained hard drives longer because large magnetic drives continued to provide inexpensive bulk capacity, especially for backups, video collections, archival files, and other workloads where cost per terabyte mattered more than low latency. The replacement, therefore, did not occur at the same pace in every kind of computer. In ultra-portable machines, removing the hard drive brought advantages beyond speed. Designers gained freedom from a component that required mechanical clearance and protection against shock. A solid-state storage module could fit into a much thinner chassis and operate silently. Battery life could benefit because there was no platter motor that needed to spin continuously during activity. The reduction in moving parts also complemented a broader trend toward lighter, quieter, portable systems. In desktops, physical size mattered less, but responsiveness remained persuasive. Users who upgraded an older machine from a hard disk to an SSD often discovered that the computer felt dramatically newer even when the processor, graphics card, and memory remained unchanged. Boot sequences that had involved long periods of disk chatter shortened. Applications that previously appeared after several seconds opened with far less delay. System updates completed more quickly when they involved large numbers of small file operations. The improvement came not merely from a higher sequential transfer rate, but from removing the mechanical seek that had dominated random access. This distinction helped explain why two drives with very different headline bandwidth could sometimes feel closer in ordinary use than benchmark charts suggested, while both still seemed much faster than the hard disk they replaced. Once access latency dropped substantially, further performance gains depended more heavily on workload. Copying a huge video file benefited strongly from higher sequential bandwidth. Launching a small application might depend more on latency, controller behavior, CPU processing, or software design. Storage performance was becoming multidimensional, and simple comparisons based on one number no longer captured the entire experience. The form factor of consumer SSDs also began to evolve. The first mainstream models often resembled laptop hard drives because they were designed as straightforward replacements. A 2.5-inch SATA SSD could fit into systems already built for 2.5-inch storage, making adoption easy. It used familiar power and data connections and required relatively little change in computer architecture. This compatibility helped the technology spread, but it also preserved physical dimensions that were no longer dictated by internal mechanics. A solid-state device did not need room for platters, a spindle, an actuator arm, or sealed mechanical chamber. Much of the enclosure existed because the PC industry had standardized around the size and mounting arrangements of earlier drives. As portable computing demanded thinner designs, manufacturers increasingly favored compact circuit board formats that removed the unnecessary shell. Among these, the M2 form factor became especially important. An M2 storage module could be a narrow board mounted directly onto the motherboard, eliminating the separate drive enclosure and cable arrangement used by traditional SATA devices. Yet M2 itself did not automatically mean faster storage. Some M2 SSDs still communicated through SATA, and therefore remained subject to the same performance ceiling as a 2.5-inch SATA model. Others used PCI Express, which gave the drive access to a much faster connection. This distinction became important because the physical appearance of storage was changing faster than many consumers understood. Two modules of similar size could use very different communication methods and deliver substantially different performance. SATA remained successful because it had been built into countless systems, was inexpensive to support, and was fast enough for a broad range of everyday workloads. A well-designed SATA SSD could deliver performance near the practical limit of the interface, commonly around several hundred megabytes per second in sequential transfers. Compared with a mechanical hard drive, that represented a dramatic improvement. Yet flash technology was capable of more. As controllers gained parallel channels to multiple NAND packages, the device could process increasing amounts of data internally. The SATA link became a narrow exit through which that work had to pass. Engineers needed a communication path more closely matched to the characteristics of semiconductor storage. PCI Express offered one. It had already become a fundamental high-speed interconnect inside modern PCs, used to connect expansion devices that required substantial bandwidth. Instead of treating storage as a separate subsystem bound to an interface designed around earlier disk technology, SSDs could communicate through PCIe lanes with far greater throughput available. Early PCIe-based solid-state products demonstrated the potential, particularly in high-performance and professional systems. The remaining challenge was not simply providing a faster electrical connection. The software protocol used to issue storage commands also needed reconsideration. Traditional approaches had been shaped by assumptions appropriate to mechanical disks, where the number of commands that could be processed usefully at once was limited by a single set of moving heads and the time required to reposition them. Flash memory was inherently more capable of parallel activity. A controller could work across multiple NAND channels and handle many outstanding requests without waiting for a physical arm to move between tracks. A protocol designed for rotating disks could still function, but it was not necessarily the most efficient way to exploit this behavior. That difference became more significant as PCIe bandwidth increased. The industry therefore faced a problem that echoed earlier moments in storage history. The new medium had inherited infrastructure from the technology it was replacing. Floppy drives had once shaped expectations for removable storage. Hard disks had introduced permanent internal capacity. SATA had modernized the connection for drives still dominated by mechanical delays. SSDs eliminated those delays, but they initially continued speaking through systems created for devices whose behavior they no longer resembled. To unlock the next level of performance, the PC needed a storage protocol designed from the beginning around non-volatile semiconductor memory rather than spinning platters. That requirement would lead directly to NVMe, where the transformation from kilobytes on removable magnetic disks to gigabytes per second on compact solid-state modules would finally become unmistakable. NVMe emerged because solid-state storage no longer behaved like the devices that older protocols had been designed to manage. Its full name, Non-Volatile Memory Express, described the essential idea clearly: a communication standard created specifically for fast memory that retained data without power. Rather than forcing modern flash storage to operate through conventions shaped by rotating disks, NVMe allowed the drive to communicate over PCI Express with far lower overhead and much greater parallelism. That architectural change mattered because an SSD could handle many operations at once across multiple NAND channels. A mechanical hard drive, by contrast, remained constrained by the movement of a limited number of heads over spinning platters. Earlier command systems had evolved around that reality. NVMe assumed something different from the beginning. It was built for electronic storage capable of responding rapidly to large numbers of requests without waiting for a physical mechanism to reposition itself. One of the most important differences involved command queues. Older storage interfaces supported relatively limited queue depths because mechanical disks could gain only so much from having many requests waiting at once. NVMe expanded this concept dramatically, allowing numerous queues with thousands of commands available in each. In practice, the benefit depended on workload, software, controller design, processor resources, and the flash itself, but the underlying architecture was far more suitable for parallel computing. Multiple processor cores could submit storage work efficiently without forcing every request through a narrow path created for an earlier generation of hardware. The result was not merely a higher benchmark number. Storage communication was becoming more closely aligned with the way modern processors and memory systems already operated. PCI Express provided the physical pathway that made this possible. Instead of sending data through SATA, an NVMe SSD could connect directly through PCIe lanes. Each new PCIe generation increased the amount of information that could move through those lanes, allowing storage devices to scale alongside broader developments in computer architecture. PCIe 3.0 NVMe drives brought sequential speeds measured in several gigabytes per second into consumer PCs. Later, PCIe 4.0 models moved substantially beyond that level, and PCIe 5.0 devices pushed still higher. The exact figures varied by controller, NAND, capacity, thermal conditions, and workload, so the significance of the transition did not depend on any single record-setting number. What mattered was the scale. Personal storage had moved from devices whose performance could be discussed in kilobytes or low megabytes per second to compact modules capable of transferring several gigabytes during the same interval. The physical appearance of the technology made the contrast even more striking. A common M2 NVMe drive contained no platter, actuator spindle motor, removable disk, or bulky mechanical assembly. The visible hardware was primarily a narrow circuit board carrying a controller, flash packages, and supporting components. Once installed flat against the motherboard, it could almost disappear beneath a heatsink. The storage device had become smaller at the same time that its capacity and throughput had grown enormously. This created new engineering problems that earlier generations encountered differently. Heat, for example, remained a concern, but the source had changed. A mechanical drive generated heat partly through its motor and rotating components. A high-performance NVMe device could become hot because its controller and flash were processing enormous amounts of data electronically. Under sustained workloads, some drives reduced performance temporarily to remain within safe operating temperatures. Motherboard manufacturers began adding dedicated M2 heatsinks And airflow around these tiny modules became relevant in systems performing long transfers or demanding professional tasks. Storage had eliminated mechanical motion without eliminating the laws of physics. The challenge had shifted from controlling moving mass to removing heat from increasingly dense electronics. Capacity continued rising alongside speed. Consumer NVMe drives became available in sizes that would have been difficult to imagine when floppy disks dominated personal computing. A single module could hold 1, 2, 4, or more terabytes, while occupying less physical space than many earlier removable media cases. That increase affected software design as much as user behavior. Game developers could create larger worlds containing high-resolution textures, detailed audio, complex geometry, and extensive cinematic assets. Video editors could work with high bitrate footage directly from fast internal storage. Large development environments could compile projects while accessing thousands of files quickly. Scientific and professional applications gained practical access to datasets that once would have required specialized storage equipment. Even ordinary tasks benefited from the reduction in delay, though not always in proportion to advertised sequential speeds. A computer does not spend every moment copying one enormous continuous file. Everyday use often involves smaller requests, application processing, network delays, decompression, CPU work, and software behavior that can limit how much additional storage bandwidth is visible to the user. This explains why the leap from a hard drive to almost any competent SSD often feels more dramatic than the difference between two already fast NVMe models. The first transition removes most of the mechanical latency that shaped decades of PC behavior. Later improvements reduce delays that are already extremely short. Higher-end NVMe performance still matters enormously in workloads able to exploit it, but raw transfer speed alone does not determine how responsive every program will feel. That nuance is important because the history of storage has repeatedly been simplified into a sequence of larger numbers. Capacity increased, transfer rates rose, access times fell, and form factors became smaller, but each transition changed something deeper about the relationship between the user and the computer. A floppy disk made information portable in a form ordinary people could handle. The hard drive allowed the computer to keep substantial amounts of that information internally. Solid-state storage removed much of the weighting caused by mechanical access. NVMe then redesigned the path between the storage medium and the rest of the machine so that flash could operate closer to its actual potential. These changes altered expectations. What once counted as rapid loading eventually became unacceptable. A delay that users tolerated for years began to feel unusually long after they experienced a faster system. Software evolved around those expectations. Operating systems became more aggressive about indexing, caching, updating, and managing background tasks because storage could respond more quickly. Developers began designing applications with the assumption that high-speed solid-state storage was increasingly common. Modern game consoles and PCs made fast storage part of the discussion around asset streaming, allowing software to retrieve large amounts of data during gameplay rather than depending entirely on long loading screens or keeping everything possible in memory. The boundary between storage performance and application design became less obvious because the drive was no longer merely a place where files waited between sessions. It was becoming an active participant in how quickly complex digital environments could be assembled and delivered. Yet magnetic hard drives did not disappear. Their continued presence reveals another recurring pattern in technology. Superior performance does not make every older solution immediately irrelevant. Hard disks remained economically attractive when the main requirement was enormous capacity at relatively low cost. Backup systems, network storage, media archives, surveillance systems, and large personal collections could still favor spinning disks because access latency mattered less than the price of storing many terabytes. In data centers, both magnetic drives and various forms of solid-state storage continued serving different workloads. The PC market therefore did not move through a simple sequence in which one invention completely erased the previous one. Technologies overlapped, specialized, and found new roles as their relative strengths changed. The floppy followed a similar path before becoming rare. For years, it remained useful even after hard drives had become standard because removable software distribution and simple file transfer still mattered. Optical disks later assumed many of those roles by offering far more capacity. USB flash drives and internet distribution eventually reduced the need for optical media and everyday software delivery. Each stage reorganized the storage ecosystem, rather than replacing every older format at once. The same principle continues with NVMe. It dominates performance-focused internal PC storage, but SATA SSDs remain useful in systems where compatibility and cost matter more than maximum throughput, while mechanical disks continue to serve capacity-heavy workloads. Looking back across the entire development of personal storage, the magnitude of change becomes easier to grasp through a single physical comparison. A A 5.25-inch floppy disk was large enough to hold visibly in both hands and required a drive containing a motor and mechanical positioning system. Its capacity might be measured in hundreds of kilobytes. Later, 3.5-inch disks made the format sturdier and eventually offered 44 megabytes in the high-density form familiar to millions of PC users. A modern NVMe module can be physically smaller than those disks while holding terabytes. The difference in capacity is not a modest generational improvement. It spans orders of magnitude so large that direct intuition becomes difficult. The speed gap is equally profound. A floppy drive transferred data slowly enough that the mechanism itself was part of the experience. Users heard and waited for each operation. Contemporary NVMe storage can move billions of bytes per second under suitable conditions, and many transfers finish before a person has time to consider what the hardware is doing. Latency tells another part of the story. Floppy drives and hard disks required physical movement to reach information. The system might know exactly where a file was located, but the mechanism still had to place a head over the appropriate region and wait for the correct data to pass underneath. Solid-state storage changed that relationship by replacing mechanical positioning with electronic access. NVMe then reduced the communication overhead surrounding those electronic operations. The chain between request and response became shorter, more parallel, and better adapted to modern processors. The contrast reaches beyond specifications because the old storage environment demanded direct human participation. People organized disks in boxes, wrote labels on them, protected them from damage, inserted them when requested, and learned to recognize the sounds produced by drives. Storage was visible. It had weight, texture, and a physical presence on the desk. A collection of software could occupy an entire shelf. Modern internal storage often disappears completely from everyday awareness. A user may purchase a computer containing several terabytes and never see the device holding the data. Photographs accumulated across years, installed applications, operating system files, personal projects, music libraries, saved games, and important documents can all reside on a board hidden beneath other components. The extraordinary engineering becomes noticeable mainly when something is slow, full, or fails. That disappearance is itself evidence of technological maturity. Storage became so fast, compact, and reliable in normal use that users increasingly stopped treating it as a process they had to manage moment by moment. The next generation will continue confronting familiar pressures. Manufacturers will attempt to increase NAND density, improve endurance, reduce controller overhead, lower power consumption, manage heat more effectively, and provide greater capacity at lower cost. Newer PCI Express standards will make additional bandwidth available, though practical benefits will continue to depend on whether real workloads can use it. Advances in packaging may place more memory into smaller spaces. Controller algorithms will become more sophisticated as cells store increasing amounts of information, and error correction grows more important. Other forms of non-volatile memory may eventually find roles where the balance of latency, endurance, density, and cost justifies them. None of these developments guarantees that one technology will dominate every form of computing. Storage history suggests the opposite. Different solutions survive. Because the fastest device, the cheapest device, the most durable device, and the highest capacity device are not always the same product. What remains constant is the pressure to reduce the distance between a request and the information it seeks. That pressure has driven personal storage from physical media, exchanged by hand toward electronic memory, communicating directly across some of the fastest pathways inside a computer. The journey began in an era when a user might wait beside a floppy drive while a small program loaded from a disk containing less data than a modern photograph. It passed through hard drives, whose spinning platters turned permanent storage into a standard part of the personal computer, then through solid-state devices that removed the mechanical delay users had accepted for decades. NVMe completed another stage of that transition by abandoning communication assumptions inherited from rotating media and building a storage architecture around the speed and parallelism of non-volatile memory itself. The result is a machine that can retain more information than generations of earlier PCs combined and retrieve much of it with almost no perceptible hesitation. From the audible movement of a floppy drive to the silent operation of an NVMe module, the history of PC storage is therefore more than a story of shrinking hardware and expanding capacity. It is the history of engineers repeatedly shortening the time between human intention and digital response. Every breakthrough removed another obstacle: limited space, awkward portability, mechanical seeking, slow interfaces, inefficient protocols. What once required patience, physical handling, and careful planning has become nearly instantaneous. The storage device has moved from the foreground of computing into the background, not because it matters less, but because decades of engineering have made its most remarkable achievement feel ordinary. A magnetic disk once taught the personal computer how to carry information, A hard drive taught it how to keep that information close. Solid-state memory taught it to find data without moving. NVMe taught it to deliver that data at a pace suited to the modern machine. The distance from kilobytes to gigabytes per second is measured in numbers, but the deeper achievement is measured in waiting time that has almost disappeared.